Hi everyone, this is Brian Wenzel, and welcome back to my third and final presentation for my capstone project, Redeployment Optimization at a Consumer Packaged Goods Company. For those of you that might have skipped ahead and missed the first two videos and just wanted to come to the final video, I'm going to go over a quick refresher of the problem and kind of bring you up to speed of where we are now. So I work at a consumer packaged goods company, and with COVID-19, demand for our products has continually outpaced supply. Now, what we need to do is provide recommended stock transfer orders, that is, moving inventory from one distribution center to another distribution center, to meet weekly demand and prevent stockouts. And our approach to this was using linear programming, more specifically an optimization in pulp, with an objective function to minimize the total cost, taking out the current inventory positions, the current forecasted demand, and the current supply schedule, as well as inter-warehouse transportation modes, times, and costs. Now, since this is the final presentation, I'm going to walk through all the complexities and accomplishments we've finished in this presentation, or in this project. Taking into account the 4 distribution centers, each of which could ship and receive different products, we took into account 2 different modes of transportation, truckload and intermodal, which would be by railway. We have differing speeds of arrival for each of the modes of transportation, the option and cost of a stock out, that is to not deliver products from one DC to another and short the customer. Taking into account multiple weeks of requirements, and newly with this one as well is taking into account over 14,000 unique products. So previously, we'd only done a single optimization. And again, to catch you guys up to speed, this is what that might look like. So we have a problem, which is characterized in our material data frame, as well as a list of possible lane solutions to solve that problem. So if we look at our material data frame, if I was a human, and I am a human, and to solve this problem, what I need to do, right, as a supply planner, is to walk through this, right? So at 1020 is the node, this is the plant. For material 1, we're projecting to short 50 units, right? And we need that 50 units in 3 days. So if we don't make it there in 3 days, it's a cost of $1,000 per day for every day that we're late. Now, in the other distribution centers, 1100, 1415, and 1645, we can see our available supply. Think about this as our inventory minus our immediate demand. Now, we have 50 units at 1415 and 70 units at 1100. So what we need to do is pick the option to source from one of these lanes, which is the lowest cost for our supply chain. What we can do here is look at our list of possible solutions, right? So this is just a subset of the total list of shipping lanes. And what we can first do is kind of narrow down this list, right? So maybe we have something like this, where we can ship from 1415 or 1100, because again, that's where we have supply, and either intermodal, which is by railway, or by truckload. Now, what we might first think is, well, let's just pick the lane with the lowest rate, which would be $2,075 on this lane right here, 1020 to 1415 intermodal. But what you'll notice is that's actually going to be an 8-day transit time, and we need this in 3 days. So that 5 days late would be an additional $5,000 cost because of this daily shortage cost. So what we actually need to do is continue working our way down here. $3,200 is fairly expensive for that intermodal transit. But maybe this one, right, from 1415 to 1020, we can make it in 5 days. So we're still going to be 2 days late, but it does have the lowest rate at $2,080, right? So if we think about the total cost here, it's going to be $2,080 plus then another $2,000 for the 2 days late. And if we run the algorithm, we can see that that's what happens here, right? So we're going to ship from 1415 to 1020 by truckload. We're going to ship the full 50 units there because we had the inventory. It's expected to be 2 days late at a cost of $2,081 for the lane itself, and then $2,000 for the late fee, resulting in a total cost of $4,081. Now, in the time it took me, again, as a human to explain what we just had to do there, the linear optimization could have ran through 250 of those problems in less than the time it took us. And I'm going to show you exactly what's kind of going on with the programming and walk you through the code. So let me exit out of PowerPoint here and go to our Jupyter notebook. So first, we import our packages, right? We import pandas, numpy, pulp, which is the linear programming package, and we're importing all, math, timeit, qgrid, and warnings. And I'm not going to talk about all the code. I'm just going to talk about the new segments because I've walked through the code previously in my prior video. Right, so we start our timer at the beginning. We have a shipping data frame. Remember, these are the solutions to our problems. And we have a material data frame. Now remember, this is the problem itself. And unlike our prior video, this data frame contains 250 different problems or different materials. As you can see here, we have a count of 1,000 different rows. 1,000 would be the 250 materials across the 4 different nodes or locations. So what I'm doing first is creating an optimal shipment data frame. Now this is just a blank data frame, and we name some different column headers, which we want in that final output. And different from last time, you'll notice that we don't have all of our code broken down into different chunks for the variables and the dictionaries and the problem and the constraints. Now it's all in one big segment. And that's because we actually want to run a for loop for every single unique material in that material data frame. So for every single material, we're going to create an individual linear problem that we're going to solve and optimize. And that's what we're doing here, right? So for every unique material, right, create the variables, go through the dictionaries again, create the model, run the model, add your constraints, and solve. So we're solving every single material on its own, and what we're then doing is appending those to that optimal shipment data frame we created previously, which is what you can see right here. So what we can have here is the runtime, right? How long did that take for 250 materials? We can see that it took less than 20 seconds to do that, again, which is even better than the previous time I showed you in the PowerPoint. So really good performance for this for loop and solving all these problems for these materials. And what went on in the background is something like this. Here is kind of the written form or the canonical form for the model. Here's everything that just occurred in the background. And we actually cut down our constraints. I spent a lot of time trying to write these more optimally for better performance. So I think we're down to about 20 different constraints now. And then again, you can see all of our variables down here. One of the outputs here is the recommended shipment data frame. This is all of our shipments where we found an optimal solution and we were going to short a material. We also have an infeasible shipment data frame. And I'll talk about this a little bit later at the end of the PowerPoint and really how planners and end-to-end managers can impact these infeasible shipments. But I think it's helpful to kind of talk about what that is, right? So if we look at the infeasible shipment data frame, we notice that material 44 was infeasible. Let's try and figure out why, what that means, right? So if we go to the grid of material data, and here I'm just filtered to just material 44, and you'll notice that we're projecting to short 7,651 units at node 1645. Meanwhile, we have less than 1,000 units to all the other locations. So this shipment's infeasible because there's no way we're getting product in time to 1645. There's no combination or transportation lane that'll get that material there because it's just not in our network. And again, we'll talk a little bit later about what we can possibly do about something like this. Other than just the infeasible shipment, we have the recommended shipments, right? These are all the shipments that come out of the total data frame where we found complete options, optimal options. And finally, the last thing we do is build the transports. So just because we found an optimal shipment, it might be for a really small quantity, such as 50 units, right? What we want to do with that 50 units is then group it with other materials, so not just material 1, but also material 2, if it's on that same transportation lane, up to the truckload capacity. So that's what we do down here. And you can see we basically create a pivot table, grouping by receiving plant, shipping plant, and mode. Again, removing the material, as long as it's the same receiving plant, shipping plant, and mode, we can group that shipment and try and further reduce cost. And that's what you can see down here. So from 1415, or sorry, from shipping plant 1415 to receiving plant 1020 truckload, we can group a number of materials up to 347 pounds, and I'll get them on the same truck, right, or the same lane, because it's less than the 38,000 pounds. And then down here, I just have a function, or sorry, not a function, a print statement to say the total cost of the whole linear program, what would it cost to optimally ship all of these things. Now, I just showed you running this for 250 different materials. What I'd like to show you is running this for the 16,000 materials, which might be in the entire network, right? So as we really try and expand this problem, we have 64,000 different rows here. And again, when we think about rows, it's a material at the 4 different locations. So it's 16,000 materials at the 4 different locations. And I'm going to skip all this again. It's the same code. I'm just going to run the runtime. We were able to run that optimization for 16,000 materials in just 20 minutes, which again, I think is really good performance compared to what's currently going on. So as I bring up what's currently going on, let's hop back to the PowerPoint. So I'm going to actually go down here to where we left off. Again, as I mentioned previously, we're able to successfully optimize 14,570 materials in just 20 minutes. And you'll notice that this is less than the 16,000 because we weren't going to short all 16,000 of them, right? We probably had material there that could perfectly cover demand. This is just the ones where maybe we weren't able to cover demand in time. So what does the algorithm do, right, at scale? Let's try and visualize this. Well, for 92% of the materials, we were able to send them without incurring a shortage expense, which I think is really impressive. So for 13,396 of those materials, we were able to ship them with no cost at all, as shown by the histogram down here. You can look at the other bins as well, right? Only about 478 of them were about to be a day late, and even less than that for 2 days late, and so on. So now that we know we're not having many shortages, what about optimal lanes? Are we choosing the most least expensive lane? And here's kind of the best way I could think of to visualize that. So I have a heat map of the data frame of shipping cost up here on the top, with the more favorable, the cheapest lane combinations, or shipping lane mode receiving plant combinations highlighted in dark green, and then the most expensive shipping plant lane receiving plant mode combinations in dark red. So what we want to do is more often choose these light or dark green colors. And as you can see down here, with the logistics of material shipped, this is just a count of all the shipments by material. We can see that the highlighted in orange are the heat map, right? Now what that says is we're consistently choosing the lower cost lanes. Given all of our constraints and all of our shortage parameters, we're still consistently choosing the lower cost lanes, which is fantastic. Now, I'm not able to share any kind of cumulative financial information about what this means for my company, but I am able to share time savings. So what I want to share was current process and how this is going to impact that current process. So this is an email I'd received from a coworker kind of starting this project. So all of our data comes from one source in SAP, the days of supply comes from another source in SAP, and all of that's been automated by an automated data pool. We then used to pull this data every Monday and send it to the end-to-end managers and supply chain planners for review. And what they would do is review all that information, that raw data, as we kind of went through at the beginning of this presentation, and they'd key in for every single STO what needs to go, and then a deployer, which is another resource at McCormick, or the company I'm working for, they would need to key in exactly how much needs to be sent, right? So this whole thing is a really, really time-consuming and labor-intensive process, right? And what we can do is use linear programming like this and actually reduce time by 99%. We can save a projected 1,000 hours over the next fiscal year, and we can avoid hundreds of inevitable user errors. And they might not be user errors, but just non-optimal decisions being made by using linear programming like this. And again, what we used was a combination of Python and the package pulp. Now, one thing I talked about previously was we found all those optimal shipments, but we also found those infeasible shipments, right? These are ones where we didn't have the inventory, or maybe it couldn't get there in time at all. And what we can really do with something like this is reappropriate the supply chain planners or the end-to-end managers' time. So instead of spending thousands of hours keying these things in, maybe we could have the supply planners work with the customers, right? And let them know ahead of time, we're thinking we're going to short your order. Is there a substitute product maybe we can ship you instead? Or maybe instead of that, if we can air freight the inventory from one of our suppliers, we get it there in time. And that way we could fix some of these infeasible problems by things that the linear programming optimization really couldn't find. So again, this whole thing could result in a 99% time reduction, thousands of hours saved, and hundreds of more optimal decisions being made. And with that, I'd like to open up for some questions and feedback. So as always, feel free to email me. My UMBC email address is right here, and I'll store all the fake and kind of made up data sets on my GitHub, which can be found here. And thank you so much for your time.